Welcome to this further part of the tutorial series on writing a surface shader, and I wanted to cover two things in this tutorial. The first is to make a point which I should have made at the beginning of this tutorial series, which in constructing the wood planks shader I've been seeking to demonstrate how a shading network fits together rather than necessarily the most efficient way of producing this particular shader. And in fact, the most efficient way to produce this shader is to use a node called the Bricker node. And I've reconstructed the shader using a Bricker node, and that's in the download file. The Bricker node is one of a number of nodes which are found here on the Patterns submenu, and these can be very useful in building up your shaders without having to write your own complicated VOP networks. Most of these are also pretty well anti-aliased, and that's true of the Bricker node. I'll just show you what it looks like when we render, so I'll apply it and then take a render. And as you can see, that's pretty much producing the result we want. One thing I wanted to cover is an error that's crept into the shader we've constructed so far. And we can see this if we have a look at this video of a patch shaded with the shader coming closer and closer to the camera. So it may not be that easy to see in that video sequence, but here I've got a single image from that sequence which I'm zooming into, and we can see that some of these lines, these grid lines, are thicker than they should be. And the reason for that is because our filtering is not set up correctly. So I wanted to take this opportunity to say a little bit more about filtering. And the first thing I'm going to do is say a bit about how the filtered step node actually works. And then we'll go on to look at why, in this particular case, we've got a problem. So before we start looking at how the filtered step works, just to say that this is rather a technical subject and you don't need to understand it in order to write most shaders, but it's useful if you're going to write very advanced shaders. So to write a filtered function, a filtered shader, you need to be able to calculate the area under the curve that represents your shader output. And the reason I'm looking at the filtered step is because it's a very simple curve, and the calculation of the area under the curve is also pretty simple. Another word for the area under the curve, by the way, is the integral of the curve. So here we've got our step, and we can see that we have two values of s, which is the value we're putting into our function in this case, and we want to work out the area under the curve between s and s1 and s2, and then we'll want to divide that by the difference between s1 and s2 to get the average value of the curve between those two values of s. And this is what we need to do with micropolygon shading. We'll have one value of s at one side of the micropolygon and another value of s at the other, and as we saw in the earlier video, what we need to do is work out the total amount of light, in this case represented by the step function, being emitted over that range and divide it by the range. Now, in fact, it's, as I mentioned, very simple to work out the area under a step curve like this, and the result is given here. And what we do is work out the total area under the step curve at S2 and subtract the total area under the step curve up to S1, and obviously the difference between those two things gives you the total area of the step curve between S1 and S2. So how do you know what the values of S1 and S2 are? Well, in order to know what S1 and S2 are, you need to know how much the value of S varies across your micropolygon. Unfortunately, Houdini provides a function which tells you this, called filter width. And this returns the amount that any quantity, in this case S, but it could be anything, varies between one micropolygon and the next. So in general, to calculate S1 and S2, you divide that filter width by 2, subtract it from the current S value, the S value for the current micropolygon, to get S1, and add filter width over 2 to the current S value to get S2. And what we're doing here is assuming that the value of S that we get with our micropolygon represents the value of S at the center of the micropolygon, and that tends to produce the best filtering results. So how does Mantra actually go about calculating the filter width? Well, let's assume that Mantra is rendering a grid of polygons represented in this diagram, and we've got a quantity that's varying across those micropolygons called S. Now, for the sake of argument, let's have the starting point of one of the micropolygons at 0.9, the next boundary at 1, and the boundary after that at 1.1. And in this circumstance, it's pretty easy for Mantra to calculate the filter width. It just compares the value of S at one micropolygon corner to the value of S at the next one. So the filter width across each of these two central micropolygons is 0.1. But what happens if the input quantity that we're examining using filter width has been through a frac node? The frac node, if you remember, converts a number into just its fractional part. So 1.45 becomes 0.45. So here 0.9 stays the same as 0.1 as 0.9. The value of 1 at the next boundary, however, becomes 0, and then the next value of 0.1 also stays at 0.1. So how does Mantra now calculate the filter width? Well, it looks at one corner of the micropolygon and finds a value of 0.9, and it looks at the other corner of the micropolygon and finds, or rather the corner of the next micropolygon, and finds a value of 0. So it's going to think that the value of S, or frac S, is changing by 0.9 between these two micropolygons, and thus it's going to produce a filter width of 0.9 rather than the correct filter width, which is still 0.1. And this problem exists for any kind of function which produces discontinuities. So a frac function or node, an if statement which sets different values depending on a condition, a mod function. These are all things which can cause filtering to mess up. So let's look now at how that applies to our shader. So if we have a look at our existing shader, we can see we've got a lot of rather difficult nodes for filtering. We've got some if nodes, some frac nodes, we've got a floor node up here, and these are all feeding in to the test values in our filter steps. And the test value is the thing that internally the filter step is taking the filter width of. So we can see immediately that this is going to produce some challenges for filter step filtering correctly, and that's why we're getting those odd effects when the patch is very far away from the camera. And the solution to this is to replace our filter steps with a filter pulse train. And the difference between a filter pulse train is that it can work with values outside the range 0 to 1, and it simply repeats the pattern for each integer range. So you get a flat area and a step in the range 0 to 1, it returns to 0, and you get another step in the range 1 to 2, and so on. So as before, we're going to put one of our we're going to put the multiplied value of gap width into one of our pulse trains. I'm going to get another pulse train, and we're going to put the unmultiplied value. And we can delete these two filter steps, and we can feed the values of the pulse train to our minimum, like so. And we can delete the if node, and the compare node, and the frac node in each case. We still want to keep this add node because we want to continue to jitter the planks. And the floor node here may cause us some problems with filtering, but it will probably be not noticeable. So we need to take the sum and feed this into the test value of one pulse train, and we need to take the unadjusted S value here and feed it into the other pulse train. And let's just see whether that now renders correctly. And we're getting a white image there, and I suspect that's because we haven't applied the shader correctly. So let's go up to the shop level and just drag and drop this onto my grid, and let's try rendering again. And we see we're getting mostly dark material with these small dots, and the reason for that happens to be that our pulse train works in the inverse way to the pulse, or filter step rather. So we need to take the complement here, because we want the bump area to be, in fact, our gap. So let's take the complement again of this, and taking the complement means taking 1 minus the input value. So if we do that, we should find that we're getting the correct values. Looks like I may have the multiplied and non-multiplied versus the gap width the wrong way around. So let's try putting that one down here and this one up here, and try again. That's better. There's one more thing that I need to change before trying out a render of this on a very small patch, or a patch that's very distant from the camera. If we have a look at our pulse train, for some reason, by default, when you lay down a pulse train or a filtered pulse train, you get this blur width of 0.3. Now, as I mentioned in the earlier videos, in general you want this to be 1, unless you're trying to achieve a particular blurry effect. So we'll set this to 1. And let's just make sure that this is applied to our grid, and I'm going to put the grid a long way away and see whether it renders well. And there we have it, and as you can see, that's pretty well anti-aliased. There's very little problem with the gaps there between the planks. So that's how to correct the aliasing problem we had with our shader, and also how to build the same shader more efficiently using the Bricker node. I hope that's been helpful.